Now remember that on same vector space, we can define two inner products. It is very important. On the same vector space, we can define two inner products. It is not like that a particular vector space will be inner product space under only one single inner product. We can define separate inner products on the same vector space, and in that case, the said vector space will become two different inner product spaces. So this particular statement is important for your MCQ type of problem. They may ask you whether we can define two different inner product, more than one inner product on a same vector space or not. So the answer is yes, we can define. Now let me give you an example. The example is present in the book, so from there I am choosing. Suppose for two functions, I am considering the vector space C01. Once again, that L2 space I'm considering. On this, I'm defining one inner product, which I have already shown that in the previous session, that it is the inner product space. This L2 space is the inner product space under the inner product that I have written over here. This is my first inner product that I'm defining over there on L2. The second inner product that I'm going to define is the following. You can easily check by similar sort of argument that this is also a kind of inner product. Same argument, we can show that it is also an inner product defined on L2. Actually, we are defining two inner products. We define two inner products. One is 1 and another is 2, like this. Now there is a particular special thing that is going to happen over here. Take two functions fx and gx as follows. We are considering a function fx which is a continuous function. Gx is equal to x square, which is a continuous real valued function. Here also I am going to consider two functions. One is fx, which is x, and another is gx, which is x square. Now if I try to find out the inner product between the function under the first inner product, we will get t multiplied by t square into dt, which will be equal to t cube by integration 0 to 1 t cube dt, which is t to the power 4 by 4 integration 0 to 1, which is 1 by 4. Okay, no problem. If I want to integrate that one, f comma g, under the second inner product, you will get -1 to 1 t square dt, which would be equal to -1 to 1 t cube dt, that is equal to t to the power 4 by 4 -1 to 1, and that would be 1 by 4 minus 1 by 4, which is equal to 0. So for the same pair of functions taken from same vector space, when we consider the inner product of the two functions, we calculate the inner product of the two functions with two different inner products, we get two different results. Why this example is important is of the following fact. We say that under the inner product under the inner product of the type the functions f and g are not orthogonal, but under the inner product of the type 2, the functions f and g are orthogonal. What is the definition of orthogonal vectors? This definition of orthogonal vectors can be defined with the help of inner product in the following manner. Let V be an inner product space. V be an inner product space. Vectors x and y in V are orthogonal, or we say geometrically they are perpendicular. Okay,
product is 0.
If x comma y greater equal to 0, the inner product of x and y is 0, a subset S of V is orthogonal if any two distinct vectors in S are orthogonal. Why this orthogonality is so important? Let me talk about it very briefly. Probably you have heard about the Heisenberg's uncertainty principle in quantum mechanics. What does this principle say? That if there is some sort of uncertainty in the measurement of position vector, there will be some sort of uncertainty in the measurement of momentum vector. So if the uncertainty in the position vector, uncertainty in the measurement of the position vector increases, the uncertainty in the measurement of momentum vector will decrease. Uncertainty in the position of momentum vector increases, uncertainty in the measurement of position vector will decrease. Okay. Now, and also we know from quantum mechanics that suppose a beam of light is passing through two slits, and the beam of light is actually having various components in it. It has X component, Y component, Z component. When the beam of light is passing through the slit and it's coming, it is hitting on the detector. If the orientation of the detector, and you know that these photon particles, when they're passing through the slit and it coming to your eye, these photon particles are actually has various spin components. They are rotating. This spin is the intrinsic property of the quantum mechanical particles. Okay, so when they are coming to your eyes and your detector is trying to detect it, suppose the orientation of the detector is along the direction that is orthogonal to the direction of the spin component. The spin component orientation is along Z direction, and your detector is oriented along some X direction. Now you know that X axis and Z axis, they are orthogonal to one another. So some part of that particle will be blocked by your detector, and some component of that particle will pass through the detector. Okay, and you will get a blurred vision of the photon particle. So the light will be blurred, will become blurred. Okay, it comes from it is the outcome of a very famous experiment which is called the Stern-Gerlach experiment. Okay, now orthogonality actually plays a very important role. in quantum mechanics, in physics, when we consider the two vectors are orthogonal, yeah, mathematically we understand them by saying that two vectors are orthogonal means their inner product is 0. Geometrically, we understand that two vectors are orthogonal, that means they're perpendicular to one another. But when in physics we talk about the orthogonality, we mean that they are mutually exclusive. If one component is passing, the other component is not passing. If x component is passing, the y component is not passing. When y component is passing, that x component is not passing. That is the physics of the orthogonality of the two vectors. And therefore, orthogonal vectors are actually very important in quantum mechanics. Okay. So, so remember this example that on the same vector space, we can define two inner products, and under one inner product, the two vectors are not orthogonal, but with respect to another inner product, the two vectors may become orthogonal to one another. Okay, it's a very important example, very important result. Now, since we have some time more, last problem that I'm going to discuss quickly is as follows, is also very interesting. The problem is more or less of the same type, but little bit different. We consider a vector space of this type, which is, what is this? It is the space of continuous complex valued function. Complex valued function. Remember that in complex valued function, suppose I have a function which can be written in this form. An integration of f is actually mean as integration of f1 plus I into integration of f2. This comes from the knowledge of complex analysis, and this is number A. Number B, when we integrate complex valued function and put complex conjugation, the same thing happens as it happened in the previous case. So integration f bar is actually integration of f bar. These are actually valid in complex analysis also. Okay. Define fg is equal to 1 by root 2 pi 0 to 2 pi ft gt bar dt. Okay. You are supposed to show that under this inner product, this H is actually inner product space. So let's do it quickly. Probably you have already started doing it. So first part you see can quickly be shown like this. Second part, you will understand that why have I chosen this particular problem. Okay, so I will declare at the end of the problem, not now. I'm taking a pain, do it to make the completeness of the discussion. Okay, second property is also satisfied. Let's go to the next one. Also, and bar will be there. Sorry, dt, and that is 1 by 2 pi integration 0 to pi ft bar h t bar dt, 1 by 2 pi integration 0 to 2 pi. This is pi. Sorry, my handwriting is ht bar is same as ht, and again we can interchange. As you know, these are continuous functions, and we can write it as hf, inner product of hf. And
Shouldn't it be FT bar?
Yeah, ft bar. Thank you. And the last one is ff, 1 by 2 pi integration 0 to 2 pi ft bar dt, and you know that this is nothing but is equal to mod of ft square dt, and which is always positive. And we are able to show very quickly that H is an inner product space under the defined inner product. Now I am going to introduce why. I'm going to tell you why have I considered this particular problem and why I think that it is too important. It is important not from a linear algebraic point of view. It is something which is also present somewhere in some other topic that you probably have seen or may not have seen. I don't know, or will see sometime at in some subject. Can you recall this? Can you identify this particular type of integration? Have you ever seen it anywhere in any literature or any other in any physics or any other topic? Can you identify this function in this particular inner product?
No, sir.
No. Okay. This inner product, I'm writing it once again. Integration 1 by 2 pi, integration 0 to 2 pi, ft gt, or gt, I am writing here gt, or previously I wrote ht, whatever. These are actually called, it is actually called Fourier coefficients. These are actually called Fourier coefficients, which are actually calculated by this inner product and which is directly connected to Fourier series. Okay.
Sir,
Yes.
I have a question, sir. Uh, Integration of fx dx or f dx give me area under curve. In class 12 we have studied, sir. Then ft gt dt, it what gives, sir? It means actual what the meaning of this integration, sir?
Okay, ft gt. Oh, acha, you are saying that geometrically it implies the area under the curve. FTGT actually geometrically implies what is the meaning of the product of two functions. Whose
Yes, what is the
geometric interpretation? I have to think. Right now it is not coming to my mind. I have to think before I give you a proper answer to your question. It's a very valid question, but I have to think a little bit what sort of geometry it is actually representing. Okay, the next class I will try to give that particular answer. I have to look
The
for it.
product of the two functions gives a third function.
Yeah.
And it is just the area.
No, but
it is just the area for that.
Yeah, but product of the two functions gives the third function. But suppose the product, suppose you have taken a function like x, fx is x and the gx is x square. So whenever you are calculating, so the shape of x is what? A passing through line. The shape of x square is passing through. If you consider x square only, it is kind of this curve, U-shaped curve. Then we are,
Yes,
when you are taking the product of the two functions x and x square, you get x cube. That is a different curve. It is a different function. So
yes.
that different function, the x cube function, try to draw the figure of that x cube function. Now that the area of the curve will be under that function, the product of the two functions, x cube function. The nature of x and x square will vanish from there. So if you draw x and x square together and you multiply, you get x cube. The area under the curve will be represented by the area bounded by the x cube function, not x and x square. This is one, you have said it right. That is one part. Another, in a different way, we can also put it in. Some other beautiful geometric interpretation of this type of functions are there. Right now I can't recall. Geometrically we can place it in a more beautiful way. This is one particular representation that we have said. Another representation is there that I have forgotten, and I'll try to find it out. I saw it somewhere in some book, but I can't recall right now. So if I find, then I'll definitely tell.
Okay, sir.
Okay. Who is asking?
Chandan Kumar, sir.
Chandan Kumar. Okay. Okay. And this Fourier series that I'm talking about, that this type of terms is actually calculated. This, if we can get functions, we consider these terms and we calculate them. The value, the outcome of this type of calculation is actually called Fourier coefficients, and Fourier coefficients are part of the Fourier series. Now, definitely FTGT bar, this is the more general type of function. So actually in Fourier series, we consider, in place of GT bar, we can consider two different things. Either you can consider integration 1 by 2 pi 0 to 2 pi ft sine nt dt. That is one type of Fourier coefficients that you can calculate. Another type of Fourier coefficients that you can calculate is the following: integral 0 to 1 by 2 pi integration 0 to 2 pi ft cos t dt, cos n t dt. Okay. These two types of Fourier functions, Fourier coefficients, you can calculate by considering the different forms of GT bar. And another important part is there. Why this particular in this particular integration we are multiplying the integration by this particular term? What is the relevance of this term? If I do not consider this term, what does that mean? If I consider that term, what does that mean? Okay, so this is actually very briefly speaking, I'm saying actually by multiplying by this factor, we are normalizing the vector. This is called the normalization of the vector. This normalization of the vector is there in your syllabus and will be discussed very shortly in the class after I introduce the concept of norm and orthonormal vectors, this part will be clear to you. Okay, so if I do not do not consider these factors, it means, and if I consider the integration only, it means that the vectors are actually not normalized. Normalized vectors are actually very important, and will be, why this is important, it's because of the Gram-Schmidt Gram-Schmidt orthonormalization process. Normalization vectors actually play a very important role. So gradually we'll come into that particular section. First of all, we have to define what we mean by orthonormal norm. What do we mean by norm? And then we have to introduce the orthonormality of the vectors. We have already studied the orthogonality of the vectors. Then we have to study the orthonormality of the vector. And then when we will discuss the Gram-Schmidt orthogonalization of the vector, we'll understand clearly that what do we mean by normalization of a particular vector. So here the vectors are the functions, and they have been normalized by multiplying the term by the factor 1 by 2 pi. In some books, you may find that some authors use, instead of using 1 by 2 pi, they use 1 by root 2 pi. Okay, both of them are correct actually. Okay, so that's why this integration is actually very important. This inner product space is also very important. So I think at this point I can stop now because it's already time. No more class hours is over, isn't it? Today I can leave.
Yes, sir.
Yes. Okay. Thank you so
And
much.
sir,
For,
sir, that YouTube playlist which is shared, sir, do we have to cover those portions by ourselves, or will those things be covered again in class?
What?
Sir, that YouTube playlist, calculus. So will those portions be covered again in class, or do we have to, just study from the videos?
I don't know. I don't know whether I'll be able to cover that portion once again. But it's a very good question you have asked. I wanted to discuss about that.